Okay, so we're back here for week 3. Let me give a quick summary of where we are to make sure everyone's on the same page here. So we should be finishing up, I hope, quiz number 4 today. But if you have not already, by tonight is the hope. Show you where we're at. So for our assignments. Okay, so like I said, homework 4, we're pretty much through. Quiz 4 due tonight, and then we're going to work on quiz 5, homework 6, and quiz 6 for the next week here. So that's what we're going to start today in the homework number 5 in section 7.4 will be mainly what today is, and then depending on time, I'll start to talk about section 7.5 as well for getting ready for the rest of the week here. So hopefully everything's up to date and you're understanding where we're going and what's been going on. So now let me pull up my PowerPoint here. So as we talked about, we're in 7.4 is our goal today. Not that one, sorry. Okay. So again, I want to have room to write as I'm going here, so I'm not going to go into full PowerPoint mode, or at least I'll go back and forth here at different times. So let's see. All right, so we're going to continue with the trig stuff. I'm going to keep, my little cheat sheet because I know not everyone still is there, but I'm hoping that these angles and these main sine and cosine for these angles, you got these down. The next homework is kind of a break from this. We're going to do something a little bit different, so you don't really have to know the angle measurements, and the sine and cosine of each. But of course, right after this section, we'll pick right up in that. So it's not like these are done here. But we probably won't be referring to these today very much. Even calculator, most of today's lecture is not going to involve anything about a calculator. It's just sort of more algebraic in a way, if that makes sense. So, a couple things. We're going to talk about identities. Now, if you recall, I've gone over identities with you already in the past, as in we had a number of identities where sine square plus cosine square equals 1, etc. The idea here is we're going to be proving things. We're going to be proving one side of an equation equals another by using identities and definitions and a little bit of algebra to kind of manipulate equations to make them equivalent. We're essentially proving two sides are equal. So if you recall back, a long time ago, you probably took geometry, like in high school, and you had those problems where they said, okay, given that this, and this happens, prove that this angle equals that angle, something like that. And you'd have to go through this process, sort of proving and showing your train of thought of, okay, I can add these up and that's going to be this. I can take this one equal to that. These are making a triangle. And you had a whole process where you would list the steps and sort of justify each step that you're doing. Those are the proofs that you had to do back in the day. Well, these are bigger proofs. And the good news is you won't have to show the explanation. I'll do that here in the beginning just so that you're clear where I'm getting it from. But mainly it's just a case of going line by line and making one side equal another. That's what we're talking about with trig identities. So we're going to establish identities, which is essentially proving things one side equals to another. So they're identically equal if every single thing is true for every variable. So if it's two functions, it means it doesn't matter what variable x you plug in, it'll be true for every value of x. In our case, every value of theta. It doesn't matter what angle you give me, the one side will be equal to another. That's what it means by two sides are identical. So a little refresher of some of the identities you've been given. And these are going to be sort of the core of what you use. These are the tools we're going to be using. So you knew these from before, but a little reminder. Tangent equals sine over cosine. Cotangent is cosine over sine. These are our three pairs of reciprocal identities. And of course, it stands to reason that sine equals 1 over cosecant, just like cosecant equals 1 over sine. All right, so you have these, and then of course you have your Pythagorean identities that you have over here. The first one is the one you're going to use a lot. You'll use this second one once in a while. Not so much this third one, but it is important. It will come up a couple times in your homework. Not so much as I mean going forward when you go into calculus. The even odd identities, now these will come into play once in a while, and you're only going to worry about them when you see a problem that has an angle with a negative in there. You almost always are never going to go from there to there. It's usually that you see in a negative and you want to rewrite it as that just so that there's no more negatives. And unlike the other identities, let me go back a screen here. For these identities, they work both directions. You can take a tan and you can rewrite it as a sine over cosine, or you can see a sine over cosine and make it into a tangent. This is true for every one of these identities, including these these Pythagorean identities up here. There's going to be a time where you're going to see a secant square and rewrite it as tangent squared plus 1. And another time you're going to see a tan squared plus 1 and say, no, I'm going to write it as a secant square. Okay? The even odd identities, on the other hand, those generally, you don't have that case where you're going to go from the right to the left side. You almost never want to make a negative angle inside. It's usually the other way around. So that's one of my exceptions that I would tell you. Okay, so that being said, that's again the foundation of everything that we're doing here. We're using these random previous known identities that I call them, just to make sure that we're all using the same things, and then we're going to try to use that to prove sides equal. And you'll see what I mean when we get to the problems here. So your 4 basic steps, and I'll go back and forth to this, and you'll see this at the end, kind of a refresher, or a review at the end, so you can see what's going on. Rewrite them in sines and cosines. That's going to be a technique. It's a method we're going to use. All right. You'd like to get a multiplied numerator and denominator by a ratio of a ratio by a well-known 1. I'll talk about what that means in English in a second. And then single ratio if you can. Now, what this means when they say ratios, they just mean fractions. So if you ever get multiple fractions adding together, you always want to try to make them a single fraction. Get a common denominator, put them together. Then, of course, factoring and canceling, some of the things we're going to be doing here. Okay, so, all right. So a couple of these here, we're going to simplify these. Now, I'm not going to stick to these too long. I just want to get you, this is just to get you to understand what it means when you're moving things around. But the first one, if you have tangent over secant, that's the expression you're given. What you're going to do is you're going to rewrite this thing a little bit. So I'll actually go into full slideshow mode so you're not going to see everything. Oh, not that one. Sorry. Go through the whole thing real fast. Not too many slides. Okay, so tangent and secant over secant. All these we're going to go. So starting with tangent over secant. The idea is that this can simplify. You may not realize it, but you can rewrite these. And one of those instructions was, if you're not sure, if you don't see an easy cancellation, rewrite everything as sine and cosine, okay, based on our identities in that first page. So you see here, they take the tangent and rewrite it as sine over cosine. All right, that's just this. Then they take the secant and rewrite that as 1 over cosine, and then we're going to simplify each of these things. Okay, so and something that we've done many times before, when you have a fraction divided by fraction, you multiply by the reciprocal of that bottom. And notice they're going right to that step. They're not going to put that extra piece in there because we're going to get big problems. We don't have time to write everything. And then, of course, the nice thing is the cosines cancel, and this whole expression equals sine. That's our goal, is to simplify these things, or later on you'll see a problem that says, show that this equals that, prove this identity, and you have to take this and you go through all these steps right here just to make the two sides equal. Okay, so that's the whole section right now is all about rewriting your identities with a better format. Simplify, cancel, reduce, whatever. Just try to notice how you can manipulate these trig functions and you can make things happen. It really may seem complicated because we're just learning this, but you'll find in Calc 2 especially, you can use trig functions to really simplify things that you just can't do with regular x functions. So here, different kind of case here where we have a sine over 1 minus cosine and we want to simplify. Now, first thing you're going to notice is I got two terms down here at the bottom, more than one term. So if you have one term, you can do a lot with the problem. I can split a fraction up, I can reduce things down, no big deal. When you have two terms, you have to think of it as that denominator down there is like one big term together. You can't work with part of it. You can't get rid of the cosine or work with the one, independently. They are together. It's like a factored piece. So you either cancel the whole thing or you multiply the whole thing, but you can't do anything else with it. So that's whenever you notice there's more than one term on the denominator, the bottom, that's when you're going to have to pull out some extra tricks here and, simplify these. So the technique here is, you remember from before, we learned about the conjugate. Most of the times when we're trying to rationalize a square root or an imaginary number, we're going to use that same thing here. So all these things I'm showing you right now, these are kind of the tools you're going to start guessing with. Okay, I equate this to, it's like you've got a screw that you're trying to untighten, and you got 7 screwdrivers in your set and you're not sure which one to use. You just go one at a time, and one of them is going to work here, and that's what we're trying to do here. We're trying to figure out which tool, which technique is going to work. So the conjugate, you see here, I take the original term. This doesn't stay, this stays the same. Okay, but I take the bottom, and the conjugate is the exact same thing, but you change the plus minus to the opposite. So I take and I multiply both top and bottom by the 1 plus cosine. That's the old rule of whatever you multiply by, this has to equal 1. It has to be the same thing on the top and the bottom. That way you do not alter the value of the equation, of the fraction there. So in doing this, remember what happens. The main goal is the bottom is sort of messed up for us. So when you FOIL all this out, now I didn't FOIL the top, just going to leave it factored. But the bottom, you're taking this times this, it's the difference of two squares. Or you FOIL it out, you're going to get 1 minus minus cosine theta plus cosine theta minus a cosine square. The middle terms cancel, and we're left with this 1 minus cosine square. Now, if you look at the original and you look at this, most of you will say, well, it doesn't look like it's any better. It looks actually like it's worse. And it is. It's more complicated, but there's a reason why we multiply by the conjugate. Something good is going to happen, right now. And our goal is, if I can make that bottom denominator be one term, I'm okay. So it started out as 2 terms, still is 2 terms, and it's still 2 terms here. Okay, so it didn't look like it did much good, but now is when you start thinking about what you have in the tool bag here. You have your identities, and see if you can figure out where I got this from. And I'll write it up here on the side. It's one of the identities that I showed you earlier. Remember? Sine square theta plus cosine square theta equals 1. I can take and leave the sine square over here, and I move the cosine over, and it becomes a 1 minus cosine square. All right, what's nice about that is it's a direct substitution, as I was saying earlier. We have this right here on the bottom. So I replace it all with the sine square. That's what we now have on the bottom. So all of this steps right here with the conjugate was all to somehow magically create an exact identity on the bottom, which then was replaced to make it a single term. And then now we have a sine and a sine square. It's like, remember that sine square is like having 2 sines on the bottom. So one of them cancels off, and we're left with just a single sine. And now we're left with 1 plus cosine over sine, and that's the goal right here on the first one. It's just to show that these are equivalent. Now, what they really wanted you to get was, they just want you to reduce this thing, simplify as best you can. If you can make the bottom into one term, that's a good win. That's a goal that you can try to shoot for. Okay, any questions on that one? And I'm sorry, I forgot to turn the chat on, so I'm not seeing if any of you are chatting with me. Now I have it on. Okay, and again, just holler out if you have a question for those of you in class live here. All right, next example. We have even a more different problem. We have cosine squared minus 1 all over tangent cosine plus tangent. So as you go through this, you have to kind of look and see what you have here. Okay, so I'm going to leave this up here for a reason to show you. Got to be careful. When I see cosine square minus 1, that's not the same as 1 minus cosine square. They're close, but they're not identical. So we'll get to that in a second. Just be aware that it's close. There's a similarity, and you'll see where it comes from in a second. So instead, what they did was on the top and the bottom, they factored everything, which is yet another option that you have is factor top and bottom. When you see this, you treat this like an x squared minus 1 on top. If you saw x squared minus 1, you would rewrite that as x plus 1, x minus 1. That's the exact same thing they did here. Okay, cosine squared minus 1 is cosine theta plus 1, cosine theta minus 1. Pretty much going backwards from this one. Similar, not exactly the same. Okay, on the bottom, there are two terms. There's a tan cosine and there's a tangent. So you remember your first step in factoring is pull out your greatest common factor. I can see there's a tangent in both. Let's pull the tangent out. And what we're left with is in the parenthesis, cosine theta plus 1. And all of that because now that I factored everything, you see those two parentheses right there somewhere are identical. They're going to cancel off. And what we're left with is just cosine theta minus 1 all over a tangent. And that's how we know we're doing something right is we've significantly simplified that original problem. It had a couple terms on the top. It had a square on the top. It had 3 different trig functions on the bottom, and we were able to reduce it down to just cosine theta minus 1 over tangent. Now, when I say reduce it down, you want to go as far as you can. You want to simplify as much as you can. Some fractions will not simplify very much, or if at all. Some of them are going to reduce all the way down like the number 1, but it's not, it's not going to be everything simplifying all the way gone. So don't feel that. Okay, Leslie, to answer your question, 7.4, no, it should have started. Sorry, we're on 7.4 now, so didn't have to be completed by yesterday. It should be just getting started for where we are right now for this week. Wait, is that right? Sorry, let me go back here, you guys. Yeah, that's what I'm doing right now. So this is something that I would recommend doing by early this week, but it's got to be done by Friday because Friday is when the 7.4 quiz is due. So that's what it is to answer your question about that. And then also, I'll look at that too if that's what it says. It should have been the start day, but if it says the end date, I will fix that. Don't worry. As soon as we're out of here in a second. Kayla is asking, how did cosine theta plus tangent theta change to cosine theta plus 1? Okay, let's go back to that one. And I'm assuming you're talking about this one here at the bottom. So remember, because it's a tan cosine. And so of these two, I was able to factor out a tangent. So it's like I'm dividing a tangent away. That comes out front of this parenthesis. And then what's left behind is, well, if I pull the tangent out of here, there's a cosine left. If I divide the tangent out of here, I'm left with a 1. That's how I got the tangent and cosine theta plus 1. It's similar to, let me give you another one here. It's like if I was to factor an x out of here, I'd get a y plus 1. And the reason is when you factor something out, it's essentially like dividing it away. And that's how I get the y plus 1 left inside. For this tangent theta cosine theta plus tangent theta, I'm going to see that there's a common tangent. And then I divide everybody by tangent because that's what I pulled out. And I'm sorry if that's kind of tight on the bottom here. But those cancel, leaving me with a cosine. And then these cancel, leaving me with a 1 because tangent divided by tangent is 1. So hopefully that answers the question you had there. Okay? So just in case, because I know some of you might want to do the homework while I'm talking, and that's okay. Let me just make sure this homework is correctly showing. Okay. So homework number 5 in section 7.4. It should be in everybody's assignment tab, but let me just make sure I didn't turn something off by accident. Okay, so homework number 5, 7.4. Yeah, it started yesterday. These don't have any due dates, so you guys should be able to see all the, at least right now, what you should see should look just like this. So if I kind of show you my screen, if you click on your assignments, now obviously some of these are old, but you should see homework 5, you should see homework 6, you should see quiz 5 and quiz 6, and they have that green arrow or the green flag because we haven't met the prerequisite yet. But these should be available right now, and the homeworks are never due. So all the old homeworks you should be able to see and go back to them without any problem. Okay, so again, don't worry if it's still not seen, showing. Yell at me after class here, talk to me, shoot me an email. I'll make sure this is showing up for all of you here. Okay, so last problem here on this little, sorry, go back. Hitting the wrong button. Okay, so we just did this one. Little review of the 3 that we've done, the simplification. Now this 4th one is another one where we just need to, clean this up and see if we can work on this. Now this is not an equation. This is just an expression. It's 2 fractions. And if you remember, one of the tips, tricks, techniques I was telling you is if you have 2 fractions, you want to try to put them together if possible. Make it into 1 fraction. Because a lot of times in these problems, you may not know where to go. Like, I'm not sure what the end answer is going to be. But if you start taking care of one problem, a lot of times you kill 2 birds with 1 stone. Like all of a sudden you've cleaned this up or you fixed this, and then it also took care of something else. And now you can see the end of the tunnel here. You can see where to go. So in this problem, what I'm going to do is I'm going to shoot for getting a common denominator. Okay, so remember how we do this. This denominator is sine, this is cosine. The common denominator is, well, if this one on the left has a sine, I need to put a sine over on this one. And then if this one has a cosine, I need to put a cosine on the other one. And you see now they have a common denominator. They're both sine, cosine. But of course, remember the rule. If you multiply the bottom of one fraction by cosine, you have to multiply the top. You have to keep a balance of the numerator and denominator in each of these. So here's what we do. So in red is what we're bringing to the problem. Nothing else has changed, but we multiply top and bottom by cosine of this fraction. And on the other fraction, we multiply the top and the bottom by sine. Then we have to clean things up. Now, the thing that they didn't show here, but remember, when you multiply the top by cosine, you're multiplying the entire numerator. I would get in the habit of putting a parenthesis around the original numerator. That way, you don't accidentally multiply just one piece by that cosine. It's everything. So look at this one, see if you can figure out what happened. First off, they now have a common denominator of cosine sine. Now, whether you call it sine cosine or cosine sine, it's the same thing. Just like the number 3 times 5 is multiplied together is the same as 5 times 3. The order doesn't matter when you're multiplying or adding. So you have a common denominator of sine cosine. Let's put it there, and then the rule when you add fractions is let's add the 2 numerators. Well, the first numerator is all of this. I have to distribute the cosine to every piece. That's how they got a cosine and a sine cosine. Distributing that denominator. Distributing that cosine. Wrong word. Distributing the cosine to everything. Then over here, it's the same thing. Let's distribute sine. So sine is going to multiply to each of these. That's where you get a cotangent sine and a cosine sine. And then at this point, now we just need to start simplifying and cleaning up. Okay, let's put all that numerator together, and maybe things will cancel, maybe things will happen. Now, it doesn't look like you can do much, but this brings in another technique. So first off, those cancel. We all see that. 4 terms on the top, but 2 of them are identical. Sine, cosine, sine are the same, but one's negative, one's positive. They cancel right off. Okay, the other part is interesting. We're down to this now, so it's slowly getting better. But remember, that cotangent, I can rewrite that as sines and cosines. Put everything when you're stuck. Rewrite every one of those other trig functions, the secant, the cosecant, the cotangent, and the tangent. Rewrite them all as sines and cosines, and then you see what happens here. So you see how they replace cotangent with cosine over sine. That becomes this. So this one piece is all that changed. It became that. Everything else in this stayed the same. And then, of course, look what happens. The sines are going to cancel off. Uh-oh, sorry. Yeah, they didn't. Let's kind of show this. I don't know if that's the same problem, but we'll do it here. We'll do it ourselves. So these sines are going to cancel off. And what you should get is a cosine plus cosine on the top. And on the bottom, you get a sine u cosine u. Now, I'm not, yeah, so we do have that right. There you go. It just was moving over. And then remember this, you're adding a cosine and a cosine, that becomes two of them. Just like you add two x's, it becomes a 2x, x plus x is 2x. Well, cosine plus cosine is 2 cosine. And then last, I can cancel. The cosines cancel right off. And you could do this if everything is factored and you only have one term on the top, no more pluses and minuses, no things added together. Cancel them off, and we're left with just 2 sine. We'll go back. Okay, so that, a lot of steps, but this is the idea that we're going to be doing. We're going to be taking expressions and using our rules, no guessing, no just making things up, using our rules, our identities, all the things you learn in algebra and geometry, put them together, and then try to rewrite certain expressions. Okay, so now this is the core of our assignment here. We're going to establish the identity. So we have cosecant theta times tangent theta. We want to prove that it equals secant. Now, generally, my recommendation is I start with the side that's more complicated. You can manipulate either side, but what you don't normally do when you establish an identity is don't move things around. Don't move things from left to right. Don't multiply things on both sides. You want to treat this like they are two separate problems, like that. And our goal was to make this one be a secant theta without touching the other side. Okay, I know that was kind of messy. Sorry about that. So you'll see it better here in the PowerPoint presentation here. So let me get rid of these and just show you what I'm talking about. So start with the left side because it contains the more complicated expression. Now, why they do that is you have more to work with. You can rewrite things. If I just look at secant, well, all I can do with secant is rewrite that as 1 over cosine, and I'm kind of done. I got nothing else I can do. But on the left, when you have multiple terms, you can start rewriting, simplifying, adding, whatever, and maybe something's going to work out nicely. So you see what happens on the left. Just this is all we're going to work on is just the left side, right? That right there. So they take that and they rewrite that. And I don't like to go sideways. I literally like to rewrite it like this. Straight down so that you can see everything that you're dealing with. And you can kind of follow a path. These are the same, these are the same. So you don't kind of lose track of where things come from. Now, I think on the PowerPoints, they do this just to save you a little bit of a headache and to keep it all on one slide, but it's the same thing. Okay, so those cancel off. You're left with just 1 over cosecant. And then, of course, 1 over cosecant is the same as secant. And that's how we were able to take this and make it into that. And we've thus proven our identity. That's what they mean by establish your identity, is just somehow make one side equal to the other side using your different steps. Okay, so that's the main core of this section. All right. Now, on this one, same kind of thing that you learned before, but you got to remember a couple of things. So remember the even odds, those identities here. When you have sine of a negative number and cosine of a negative angle, negative theta, I should say, you can rewrite those. Now, the first important step is not forgetting what it means when you have this. Okay? The square means it's the entire quantity squared. That's why they rewrote them with the brackets. So now that we can, now the next step is we use our even odd identity rules and say, well, when I get sine of negative theta, it's the same as negative sine of theta. And when I get cosine of negative theta, it's just the same as cosine. But when you square them both, the negative goes away and you get a sine square plus cosine square, which turns out from another identity, you know it's just 1. Now, there wasn't a whole lot to this one because you might have just seen it and said, oh, I already see cosine square and sine square. But this is kind of further proving it doesn't matter what's on the inside as long as you have sine square and cosine square of the same angle. As long as they're the same, you're going to be able to do this. There's your 1. Okay, so another identity here, another one of these negatives here. We have to prove that this whole expression, this fraction on the left, is equal to cosine minus sine. So as I said earlier, let's start with the more complicated one. Now the first thing is, notice our answer has regular thetas, no negatives. So one of our early steps, if not the first step, is we need to get rid of all these negative thetas. We can't have these because we need to end with those right there. So like the last problem, let's do some rewriting. Okay, so remember the brackets. And these brackets, you don't have to do them later. They're good here in the beginning, though, just so you don't forget what it means. When you see sine square of something, it means take the sine of that something and put a big bracket around it and square that. Now we can do our rewriting of our identities, of our even odd. So remember, sine of negative theta, look at all the pieces I did, becomes negative sine of regular theta. Cosine of negative theta becomes just cosine. Sine negative theta becomes negative sine of theta. And cosine of negative theta becomes cosine theta. Now you're wondering, why is there a negative? It's because the negative was already there in the problem. So that just came down. Basically, everything that was still there stays there unless you did a rewrite and then you replace it with what it's equivalent to. So now we try to see if we can clean this up a little bit more, and you'll see what we get. The top becomes sine square minus cosine square, which is not an identity. The bottom becomes negative sine minus stays as negative sine minus cosine. So now, what did they do? And I'll point this out again. I said it, but let me just remind you. When you get sine square plus cosine square, you make that equal to 1. No big deal. If you get sine square theta minus cosine square theta, as of now, that is nothing for you. There's nothing that simplifies to become. The only option is, let's factor this, and that's what they did on the top there. Okay? So, and Jason, let me answer that question again. I don't know if it cleared that up. I may not have said it enough, but this right here does become regular cosine theta. But the negative that was in front of it stays. So what's in that black box did in fact become cosine, but because there was a negative in front, that's why there's a negative there. Okay, just like if that was a positive, it would have stayed positive, but that's why it's negative. It's from the previous step. You don't just wipe it away immediately. Okay, so now that I've factored everything on the top, I also factored on the bottom, and that's a simpler one. Let's just factor out a negative 1. Factor out a negative 1, and now we're left with sine plus cosine. And then you see those cancel off completely. We're left with a cosine. Let me show you the step that they didn't show you here. And again, you don't have to write every one of these steps. This is mainly, I do a lot. I try to show a lot here in the lectures just because I want everyone to understand. But as you're getting an understanding of this, you don't need to write every one of these out. But this is where we are right now. After the cancellation, we have a sine minus cosine. The other parentheses gone. And on the bottom, remember, you have a negative 1 left. That little negative right there. So I can then just say, well, let's just distribute that over the top, and that becomes a negative sine theta plus cosine theta, no more fraction. And then you can rewrite it, put the cosine in front. And that's how they end up with that answer right there. Okay, and if you recall, that was our goal was, oh, sorry, go back. That was our goal was to make it equal to cosine minus sine. All right. So just want to make sure, did I answer your question, Jason, or anybody else? Yeah, it's just the part that I have here in this box. That's the only part that becomes positive cosine. And think of it this way, if that negative is bugging some of you, if I had a number in front of that instead of just a negative, let me just clear this off. If there happened to be, say, a -5 right here, when I simplify, I would simplify this as a cosine, but the -5 would remain out front because it has nothing to do with that negative angle inside. They're like two different things. Okay, so if you're not sure, we're going to do more of these. These even odds pop up once in a while. They're not what I consider the most important part of this section. It's just dealing with the regular trig functions that I want you to get. One like this problem is a good one. We have 1 plus tangent over 1 plus cotangent of u, and that equals tangent of u. Okay? So, couple things. I'm going to simplify the left side. My goal is to make everything equal to tangent u. So the left side, I'm going to see if I can rewrite that. So if you don't see anything, there's two options. You can try the conjugate again, which we would take, and this is what we have on the left, 1 plus tangent u over 1 plus cotangent u. Remember the conjugate was? I can multiply by 1 minus cotangent u, and same thing on the top. And that might make things work out for me. Maybe that'll make something good, but I'm going to hold on that for a second. Okay, the other option is I can rewrite everything as sines and cosines. So that's an option. Or I can write everything as you see how they did it here. They went and said, let's rewrite the cotangent as a tangent. Now, I'm not going to say I agree with this because, you're not going to, most of us don't know where this problem is going, so it's kind of a leap of faith to do this, but let's just look and see what they did, and I'll do this problem again a different way. Okay, so what happened was they rewrote the cotangent only as 1 over 1 plus tangent. Then, see if you can see how they got this one, and then I'll explain it in a second. Okay, so this is the problem. I just copied what was right above. And just on this bottom, I'm trying to get a common denominator. So I'm going to rewrite that 1 as tangent over tangent. Then I have a common denominator, and on the top I have a tangent plus 1. That's how they took this and made it into this right here. So if you're not sure where that was coming from, that was the technique they use. All about just good old common denominators, combining two fractions, two pieces together. And that's what they did there. Okay, so again, I'll show you a second technique if you're not liking this one. On the top, now, again, see if you can get this. We are dividing this right here by a fraction. So that's the same as multiplying by the reciprocal. So this, I'll kind of box it. This hasn't changed on the top, but what I did was I flipped over that denominator, so I multiply by tangent over tangent plus u. That's how you get a tangent right here. And then, of course, you see how the 1 plus tangent and the tangent plus 1, they cancel right off, and we're left with just the tangent. Okay, so that's definitely a way that'll work. Now, like I said, I didn't care for it. I didn't love it just because not always do we have that possibility. So I'm going to go and say, if I'm stuck, I'm going to rewrite everything as sine over cosine. Everyone see where I got those from. I just replaced the tangent and the cotangent. Now, another thing, this is where you have to really be careful that you're following the rules of algebra here. All the stuff that you learned and did again and again in Math 126. Now, if I look at this, I have 4 terms combined. 2 terms on the top, 2 terms on the bottom. And if you know what I mean when I say terms, terms are separated by pluses and minuses. Whenever you see a plus or minus, a new term is beginning. So if I multiply 5 things together, like say it's this, that's just one term. Whereas this is 2 terms. I just want to clarify that. That's obviously has nothing to do with this problem, but the plus minus is when terms come about, because I'm going to say terms a lot. I want you to understand where I'm coming from. So sine over cosine, yeah, it's a fraction. Yeah, it's 2 trig functions dividing, but it's still considered one term. And I say this because if I do something to one term, you technically have to do it to all. So here's what I mean. See on the top, I have a cosine on the bottom. I don't like that. So I'm going to get rid of it by multiplying on the top. I can do that if I do it here and here and here. Then I can do it as long as I do it to every term on the top and the bottom, because I have multiplied the numerator and the denominator. I mean the big numerator and the big denominator all by cosine. So what that will do is that's going to make that cancel off. Didn't look like it did a lot, but it did do something. Now over here on the bottom, I want to get rid of that sine, so I multiply by sine u. And then, of course, I have to multiply by this by sine, and this by sine, and this by sine. And then as long as I do it to every term, it'll be fine. So if you look at what's that green-blue stuff on my screen, every single term got hit with a sine cosine. And then I simplify, and you see what I have left. It may not look better, but it is. I have a sine u cosine u plus a sine u. I have a sine u cosine u plus a cosine u. Okay? Now, it doesn't look like I've got a whole lot going on here, but this is, where you have to go. And I don't even know if this is going to work out, but I'm showing you how you can clean things up a little bit. Okay? What I'll do next is maybe I'll do a little bit of factoring. On the top, I can do a sine u. I pull a sine u out of there, and I get a cosine theta plus 1. On the denominator, I factor out a cosine, and I get a sine u plus 1. Okay, so I'm getting somewhere, not exactly at our answer, but we're getting close. And maybe I'm going to do that conjugate thing again. I don't know if that's going to be better or worse, but we'll see what we get here. And part of this process, and this is where I don't want you to get frustrated in the homework, part of it is you're kind of going blind. You don't always know where these answers are going to go, but you can trust in the fact of if you do follow your steps, don't just start making up things, you're going to get some sort of an answer. You're going to get something that does work out. That's what we want. So look and see what goes on in try to write this in a better spot, but let's try on the bottom here. What we end up with on the top is a sine u, and then we get a cosine u plus 1. Let me leave it factored for now. I'm trying not to give you the worst problem to start, but this may not be a good example here. Okay, so factoring these things out, or sorry, I'm just leaving that factored. On the bottom, the reason why I multiplied by the conjugate was I end up getting a sine square minus 1. And the reason I'm doing this for now, for this beginning problem, is I just want you to see what you get. What's going to happen when you start throwing things and seeing what happens when you multiply them together, multiply the conjugate, rewrite as sines and cosines, see if something gets better. Now, what you have to be ready for is, maybe I did this and I don't like the way it's going. So I'm going to stop. I'm not going to stop here, but in my homework example, maybe I'll stop and go back and try something else. Then if that doesn't work, I'll come back, but you want to leave yourself paths to take. Okay, so let me go to I'm going to get rid of the slide for a second just so we can get more good work here. Okay, so let's go to the top here. What I'm going to get on the bottom, let me go some identity reminders. So we know cosine square u plus sine square u equals 1. So if I was to move this over, I would get 1 minus sine square. And you'll start to see that's a theme. Unfortunately, in this parenthesis, I don't have 1 minus sine square. I have sine square minus 1. That's not a problem. I can just divide everybody by negative 1 in that identity. And now I have negative cosine square u equals negative 1 plus sine square u. And that's the same thing as what we have on the bottom. Okay, so I could take this and on the bottom I end up with a cosine u and a negative cosine square u. Now the hope is, don't forget your goal. I'm going to put the goal here on the bottom left. We're supposed to be getting just the tangent u, like we proved earlier. Okay, if you're doing this and you're starting to see, okay, now it's starting to get a little bit out of hand, don't be afraid to say, okay, let's stop. Let's try something else. Maybe it's not going to work. But like I said, on identities, you have to sort of roll the dice sometimes. You have to just take a shot because you don't know. You're not expected to see the whole path all the way through. Take a couple steps. If you're feeling it's starting to simplify and regress down to this tangent u over here, then go with it. But if you see, oh man, I'm getting all this garbage up here and nothing seems to go away, hold it, take a break. Now, the only thing I want you to see right now is you look at the original problem, the very original, which was, put here, 1 plus tangent over 1 plus cotangent. Even though we didn't get the right answer, every single thing on this page is equivalent. This big thing up here, even this original one right here, all of these that I've boxed, they're all the same. They're all identities. Now, obviously, some are better than others, but they're all equivalent forms of the same thing. If you picked a u, like pi over 3, and you plugged it into any of these boxes, you will get the same result numerically every time. If you plug in 5 pi over 4 to any of these boxes in place of every u, you will get the same answer in each box every single time. So that's what we're talking about here with identities. Every one of these are equivalent. Like I said, I was hoping to show you one that also arrived at tangents, but it's actually taken me on a long course out of here. So let me get away from it for a second and give you one that'll actually work. In a nutshell, though, here's how the problem works for your identities. You're given some expression, some trig expression. And your goal is to get to some other trig expression down here. Sometimes it's a straight path. Sometimes you got to go here and then here. Sometimes you got to go all this long way and you end up over here. But as long as you're following your steps, you're eventually going to get there. That big problem I just took off the board, eventually, if I kept simplifying it, we were way over here at this point, eventually it would have gone all the way and become a tangent u. As long as you don't just start making up substitutions or making up identities or inventing new algebra rules, follow all the rules and you're going to get the answer. You literally will each time. It's just not always not visible. Okay, so kind of like if you play chess, some people can see many moves down the board. Not everybody does. Some see 1 move, some see 2 moves, 3 moves, some see 25 moves. But you have to approach this like you're playing chess, where you got to think, okay, if I do this, where will I go? What will that then do? And then where can that go end up? Am I even going to be near my ultimate goal? and even starting to work backwards. Well, I know tangent equals sine over cosine. If I get something that has sine over cosine, I know I'm on the right track. I'm in the vicinity. That's how you play these games when you start solving identities. Okay, so a couple more of these. Okay, so here's another one. Sine over 1 plus cosine equals 1 plus cosine over sine. We need to make all of that equal to, show all of that is equal to 2 cosecant of theta. So looking at the two, the left and the right side of the equation, I see the left side being more complicated, so that's probably the one that we should go. And that's what they say here. Start with your left side. It's more complicated. So now, look at how they add this. Now, they didn't write the steps, so I'll sort of squeeze them in here. What we're doing is we're looking for a common denominator. All right? I need the left side has a 1 plus cosine, so the right side needs to have a 1 plus cosine. The left side, this one has a sine, so this one needs a sine. So remember the rule. If you multiply the bottom by sine, do the same thing on top. If you multiply the bottom by 1 plus cosine, you do the same thing on this top. And then now you can get a common denominator. And doesn't cancel things off. This is your common denominator right here. I took the sine times sine to get the sine square. I took the 1 plus cosine and the 1 plus cosine to get a 1 plus cosine parentheses squared. Okay, so now let me clear this off a little bit and go to the next step. See how they get this. And again, I'll kind of leave you a second or two, or a couple seconds, just to look this over and see how, if you can see how they progress from one line down to this current one. Notice what didn't change. My denominator didn't change. All it is the top that I'm trying to combine. All right, so we're going to multiply out those numerators and then try to put everything together. So the sine square stays as a sine square. Over here, remember what 1 plus cosine is, 1 plus cosine squared is, it's 1 plus cosine times 1 plus cosine, which means you FOIL it out. You get a 1, you get a cosine and another cosine, that gives you the 2 cosine, and then you have a cosine square. That's how we got that stuff on the top. And then I combine things, and there are 4 terms up there. There's a sine square, a cosine square, a 1, and a 2 cosine. Well, they put the sine and the cosine, sine square and the cosine square together, and hopefully you know that's because sine square plus cosine square is going to equal a 1. Okay, so let me go back and show everyone how that came about here. See all this stuff on the top. We have 4 terms. Well, 2 of the terms, the sine and the cosine, they become the number 1. So now we have 1 plus 1 plus 2 cosine theta on top. The bottom is still the 1 plus cosine theta times sine. And if you're wondering, it doesn't matter if you have sine or 1 plus cosine first, as long as they're both together on the bottom multiplied together. So now from there, and that's why I wrote this so you can kind of see to the next page, we have 1 plus 1, which gives us that 2 on top. 2 plus 2 cosine theta. And then factor out the 2. So we have 2 times 1 plus cosine, and you can see it already. The 1 plus cosines cancel off. We have 2 over sine, and this should remind you, oh yes, and my goal, remember, was 2 cosecant theta, and 2 over sine becomes 2 cosecant. And keep in mind that reciprocal identity, we know that 1 over sine equals cosecant. The number doesn't matter. If that's a 10 or a 50 on top, that stays on the top. You don't flip over the whole thing. You just flip over the sine part, just the sine. The 2 stays up top there. All right, any questions on any of these steps for this establishment of the identity? I'll go back to the previous page and kind of look at how all those were. Go back. Any part of this first page or the second page, in the establishment of the identity? Anything you're not sure of? All of this. Okay, let me go back to that first slide. Okay, so Kayla, you're asking the last step, that one right here, how we got this. And from here down to here, all that happened is we have four terms on top. We have a sine square, we have a 1, we have a 2 cosine theta, and we have a cosine square. What they did was they rearranged the 4 to put the sine square and cosine square together. It didn't have to be a parenthesis. It's just the same four terms on top, just in a different order. And then, oh, I'm sorry. Okay, so then from here, all that happened is because of the identity that sine square plus cosine square is 1, think of this parenthesis is replaced with a 1, and then we have another 1 and a 2 cosine theta. And that's how this ended up right here. So that parenthesis that was sine square plus cosine square, that became a 1. The 1 plus 1 gave me this 2, and then we left the 2 cosine there. And Jason, oh, I'm sorry, I'm back. I'm sorry, the wrong one. We're already there. Not Jason. Does that make sense, Kayla? Okay. So let's go back to, or up to the next one. We have another identity. We have to prove that all of this in this fraction equals the number 1. So if you see any obvious identities, go and do them. Like if you see a sine square plus cosine square, rewrite it as 1. If you see a tan square plus 1, write it as a secant square. You know, the real obvious ones. But if you don't, you just get a big mess of trig functions. I always say the best way is let's rewrite these as sines and cosines and let's simplify and see what happens. So that's what's happening right here. All four of these trig functions are now rewritten as some kind of a sine and or a cosine. The tangent is sine over cosine. The cotangent is cosine over sine. The secant becomes 1 over cosine. The cosecant becomes 1 over sine. And that's what we get to, you know, again, it's going to make it a more complicated looking expression, but now instead of dealing with 4 different trig functions, we're now down to 2. And that's the reason they always recommend going to sines and cosines is you have 6 total trig functions and up to 6 different trig functions in a problem. If you can condense them down to 2, that shrinks your world a lot more. You don't have nearly as much to cover here. Okay, so now look what happens here. All right, look at this carefully. On the bottom, that's the easy one. We have 2 fractions multiplying together. Remember the rule for fractions, just multiply straight across. That's why we get a 1 over cosine sine down here. But on the top, these are fractions that are adding together. And you know the rules, which you're going to hear 100 times in the next couple of weeks. You need to get a common denominator. So if I have a cosine here, I got to put a cosine here. And a cosine here. If I have a sine here, I got to put a sine over here and a sine over here. So now I have a common denominator, sine, cosine, right there. And then look at your numerators. Sine times sine is a sine square, and cosine times cosine is a cosine square. So don't try to do too much at once, just do one step at a time. Now on the top, they did 2 things at once, just as I got done telling you not to, but let's look at just this right here. Sine square plus cosine square is a 1. They left the denominator the same. So this right here is this red box. Then because we're dividing by a fraction, we multiply by its reciprocal. And then you can kind of see what's happening. The cosine and the cosine will cancel. The sine and the sine will cancel. And we're left with just the number 1. So like I said, you don't always see that it's going to happen that nice and easy and clean. But these are all going to be true statements. You're not like proving something that may or may not be true. They are true things. You have to go find them. So you have to just sometimes take a step over that direction and see what happens when the dust settles. See what cancels off there. Okay, so question, Jason, the answer is that you just have to get the left side equal to the right. So we took this left side and we manipulated it. We got it down to 1. So once you get the left and the right equal, that's all you're trying to show is that the left and the right side are equal. So that's the answer. There's no answer to box. It's just a process to show that left side equals right side. Okay, and then yeah, so you don't need to write anything else. Just say you found the two equal, and that's it. Okay, so let's look at a couple more here. 1 minus sine over cosine equals cosine over 1 plus sine. Now, we always start with the more complicated side. They're both about the same, so it doesn't really matter. So in this case, what the technique is, they're going to start with the left side and multiply the numerator and denominator by 1 plus sine. Now, why do they do that? Well, here's the reason. Doesn't matter which way you went. Your conjugate is usually when you multiply the bottom two terms, but you can also do it on the top. So they're ignoring this. They're just going to say 1 minus sine over cosine. Let's multiply everything by that conjugate of the top, which is 1 plus sine. And they even put, you could have multiplied this denominator over here by 1 minus sine, that conjugate, and it would have worked. So they took the left side, 1 minus sine over cosine, multiplied it by 1 plus sine over 1 plus sine. And the idea is, see what happens. Let's not multiply this yet, but the top becomes 1 minus sine squared. And that's got to trigger in your head immediately that, oh yeah, cosine squared plus sine squared equals 1. So if I slide over the sine square, it's now 1 minus sine squared over there, which equals cosine squared. All from that Pythagorean identity right there that they wrote in blue. And now you have two cosines on the top, as in cosine times cosine, 1 on the bottom. You cancel one of each, and you're left with cosine over 1 plus sine. And that was your goal. I don't know why it says cancel there. Ignore that. So that's it. You've made the left side equal to the right side, which, remember, the original problem, it was cosine over 1 plus sine. That's what we turned the left side into with all these steps. Sometimes it's going to be 2 steps. Sometimes it's going to be 8 steps. It just depends on the problem. Okay, so the last couple slides here, the last slide, they just talk about starting with the complicated side. Try to rewrite these as a single quotient, meaning 2 fractions, try to make them as 1 fraction. Okay? If you're stuck, write everything as sines and cosines. And the last part, try to keep in mind what the other side is going to become. So don't be afraid to go back and forth. Now, the thing that I do differently than what this is doing, if I get an identity like this, my procedure, the way I do this on paper, just because I think it's easier for me to understand, is I just keep working down with this. So I would do something like, okay, I'm not even touching the right. I would write this. Okay, and then I would say, well, let's do that conjugate thing. 1 plus sine. 1 plus sine. And then I have 1 minus sine square. And you see, I'm working straight down so that I can follow my steps vertically. To me, it makes it easier to spot something. Like just now, I almost made a mistake when I caught it, but let's say I didn't. And I wrote 1 minus sine down here. I'm hoping that as I'm going through my work, I'd say, oh, wait a minute. That was 1 plus sine. Why is it 1 minus sine right here? Oh, yeah, it shouldn't be. I made a mistake. You can see things when they're all lined up a little bit better. Then I would write the top as cosine square. And then cancel that cosine with one of those. And now I get cosine theta over 1 plus sine theta. And that's exactly what I was shooting for. So I've made the left equal to the right. And that's how I like to set them up, just because I think it's easier to see if you work down vertically. It's not a requirement. It is just, what I have always preferred to do. Okay, so let's get out of this and let's do some here. Okay, so back in our My Math lab, we are on homework 5, section 7.4. So what do you see? 47 problems, kind of what the norm of what you've been getting on your homework here. Like I said, I like to just do every fourth one just to give you an idea of what, a sample of what you're going to be seeing on your homework here. Now, these are different types of problems where you're going to get some of these preliminary problems, and then you're going to get some that just, you're not going to have to write as much work as I've been showing because of the format here. But see what we have here. Suppose f and g are two functions in the same with the same domain. If f of x equals g of x for every x in the domain, the equation is called a blank. Otherwise, it's called a blank. Okay. It's an identity, equality, conditional property. Yeah. I would say identity. I wouldn't even go over the definitions. I'm sorry about that. It's a good time to learn them though. And otherwise, it's called I'm just going to guess a few and see what we get. Okay. And they actually give them to you right here. It is identity, and that other one was conditional. I was thinking that was it. But don't worry about these definitions. Honestly, this is just to kind of get you going on these. But now you can kind of see identity is when they're the same for all values. And the otherwise was not exactly clear. But like I said, don't stress about these first couple. I care about these ones where you need to go and show your identity work. Show what you know about how these things are rewritten. Okay, so determine in this particular case whether the statement is true or false. In establishing an identity, it's often easiest to just multiply both sides by a well-chosen non-zero expression involving the variable. Generally, we're not going to do that because we don't want to go and mix the left and the right side. You like to work with one side independently and then the other side independently. And the big picture, what happens is sometimes when you multiply, you create some false answers. Not usually. You're allowed to do that, but for identities, you really want to pick one side, work with that, and not touch the other side. Okay, in this one, they want us to rewrite these in terms of sine and cosine. All right, so we have a cosecant theta all over a cotangent theta. Now, make sure you follow the directions because they're literally trying to train you in how to do these. So even though some of you may be jumping ahead and doing something that's even better than this, they only want the first part. So rewrite this as a sine and cosine. Well, that's 1 over sine. And then this is going to be cosine over sine. Now, it didn't say simplify. Oh, it does say simplify. There it is. So if I plug this answer in, it's technically right where I've rewritten it as sine and cosine. But that last part in parentheses, they want you to simplify this. So this should be 1 over sine. And then remember, multiply by the reciprocal. And then that just becomes 1 over cosine. And that's what you need to enter here in this box. Now, some of you may look at it and say, well, wait a minute. I know that is the same as, that's the same as secant. And that is true. If you called this secant of theta, it would be right. Okay, I just look and see if that was a shortcut there, but it's not. Theta. It is the same as secant of theta, but that is not what they asked. They wanted to see in terms of sine and cosine. So if I put secant of theta, pretty sure they're going to give it a wrong answer, yeah, because they want it in a certain form. Even though this is better than what I just had, cosine of theta, that's the way they want it to be because of the instructions. So don't, even though the next step, secant of theta was better, that's not what they're looking for here. Okay? So let's go with number 15. Okay, so they want us to factor and simplify. Notice we're not proving identities here in these first few homework problems. We're just trying to rewrite these a little bit, see what we can get. So factor it. When I see this, top and bottom, okay, this is essentially the same as that right there on top. If you could factor that, you'll do the same thing here. So remember how to factor this. Looks like it's going to be a +2 and a +1 right here. That gives me the 2x. That gives me the 3x. There's my 5x. So it's the same thing on this one. I'm going to write 3 cosine of x +2 times, not x, cosine of x, theta. Cosine of theta +1. Now remember, if you're ever not sure if you factored it correctly, you can always FOIL this out. That times that is 3 cosine square theta. We get an outer term, we get a 3 cosine theta. Inner term, we get a 2 cosine theta. Last term, we get a 2. Those become a 5 cosine theta, confirming that was what we had. That's just how I can always check. And no, you don't have to write the whole thing out. You can do part of it in your head or some of it in, all of it in your head. Or you can write it out and FOIL it out like I just did. But that's how you can go and look and see that you actually did factor this correctly. On the bottom, we get a cosine theta and a cosine theta. Looks like it's got to be a 1 and a 1. Factor and simplify. So we factored. Now we simplify. And just like factoring before, you can only simplify identical parentheses. So I'm at 3 cosine theta +2 and a cosine theta +1. Now the temptation a lot of people have is they want to do this. Don't do this. They want to just simplify the cosines because I see one cosine on top of another. What you have to remember is these were factors. You either cancel an entire factor, like I did here and here, or you cancel none of it. There's no partial canceling. Okay? That's why I never mind leaving a parenthesis there so I don't forget. Don't cancel. Plus, there's 4 terms, a 3 cosine, a 2, a cosine, and a 1. If you cancel, you must cancel from every single one of those 4 pieces. We don't have that. So 3 cosine theta +2 all over. And again, I probably should have done this, but okay. Yeah, I did hit that fraction button first when you get some complicated stuff. And there's our answer right there. All right, so let's look at number 19. Now we established the identities. So I'll look at what I would do on the right side here. Sorry, the right side is my least complicated one. The left side seems to have more things going on. So that's the part I think we can work on. Okay, now remember, we want it to equal cosine square of u. So notice, because Jason was asking earlier, what's the final answer? There's no right answer because you're just trying to prove 2 sides are equal. So I can go and do this whole problem. Now I'll do this one right here just to kind of show you. Let's make that 1 over cosine of u. This is cosine of u minus sine square of u. These cancel off and I get 1 minus sine square u. And then I remember from my Pythagorean identity, that's the same as cosine square u. So I've proven the 2 sides. But they're not asking for every line. Well, they might, but read what they ask. This one says, write the left side in terms of left side term secant in terms of cosine u. So all they want you to do is take this one term. See, they left the cosine, they left the minus sine square u. They want you to rewrite the secant as 1 over cosine of u. That's it for part 1. You see, we have 3 parts. Part 2, simplify the expression from the previous step. So the minus sine square stayed the same. And remember how these canceled? We had the 1, what I had right down here. There's your second part. And then now, the expression in the previous step is equivalent to cosine square u. Okay, so this, they're telling you that this equals cosine square u because of the Pythagorean identity. That's a little mix of doing the work and kind of explaining how you got it, but that's the 3 parts. That's how they're going to ask you to solve these problems, how to complete these different problems. Okay, so if you can do what I'm erasing here on the right, you'll pretty much be able to answer all the parts that they ask you. You just have to make sure you completely address what they're asking. You know what they're asking, because sometimes sometimes I could see someone do these problems perfectly, but they didn't know what the computer wanted, what MyMathLab was looking for, and that's why they got it wrong. So a lot of you doing this homework is you getting an idea of what they want it to be. Okay, verify that the trig equation is an identity. Which of the following statements establishes the identity? Okay, so now this is that left to right process that I don't like, so I'll kind of do this problem. I am going to take this part, because that's what they did here in the beginning, and then rewrite this until it ends up that. So this is the start. Negative sine square x plus sine fourth of x. Okay, so forget the problem here. What I'm going to do is a couple things. Let me pull out a sine square. Okay, and generally, I'll do this a couple ways just to show you. If I factor out a sine square x, I'm left with a negative 1 plus sine square x. Okay, or I could have pulled out a negative sine square x, and that would have left me with 1 minus sine square x. They're both the same. A lot of times people don't like that first term to be negative, so they'll pull that out. And the reason to this is better is that this parenthesis is cosine square x. All right, and then remember what our goal is? Our goal is to get all these cosines, cosine fourth, cosine square. So I got a cosine square, but now I'm going to replace this with the 1 minus cosine square x, both from the identity, from the Pythagorean identity. All right, so this stays the same as a cosine square x, and that negative sticks around in the front. And then my last part is, let's distribute. I can distribute the negative first. Let's do that. I'll do 2 steps. You can do it all in 1 step, though, if you're seeing this. Let's make this a negative 1 plus cosine square x. And then I distribute the cosine square. And then, of course, I can rewrite it as cosine fourth x minus cosine square x. So I wrote a lot of steps because what I'm trying to do is I'm trying to see which of these 4 options looks most like mine. Okay, so remember, when they're doing this, they're completely looking at the left and trying to see where you go, what steps you take. So all these are the multiple steps there. So let's look at this first one. They took a negative sine square x plus sine fourth x, and they rewrote it as cosine square x, 1 minus cosine square x. Kind of a jump how you went from here to here. So I'll tell you, I'm not liking that too much. We'll come back to it if we need to. Same thing with this one. You went from here to here. That doesn't even look like an identity, I know, so definitely not going to be B. C and D are getting closer, but again, D, how do you go from sine to secant? That's not an identity, but C looks kind of like what we did. We pulled out that negative sine square x, and we got the 1 minus sine square x in the parenthesis. Then they replaced this with cosine square x minus 1. Well, it was this and this, but then it became this right here, so that matches. And the second part became a cosine square, that matches. Then they multiplied it all out to get this. See how part C looks the most like the one that we worked on. So you'll find it not that bad. What I'm going to say is don't just look at these because you're going to go crazy looking at these. They all kind of look the same. They all seem legitimate at first. It's hard to tell. My recommendation is you keep this away, you write the left side on your paper, and you see if you can go make the identity happen. Then you backtrack and look and see which one looks most like your answer, and you select that one. Okay? All right, let's look at number 27. Okay, so now in this one, this is one of these where they want you to go step by step. So let's try to work on it that way. All right, so write the left side of the identity in terms of sines and cosines. So notice this didn't change. This is the thing they want us to rewrite as sines and cosines. So over on the right here, this 4 secant theta over cosecant theta plus 3 sine theta all over cosine theta. Okay, so they said rewrite that left side. Well, this should become 1 over cosine, and this should be 1 over sine. Okay, now, I could stop this right here, but I believe they're going to want this thing to be simplified a little bit more. Okay, now, so let me test it out. And this is, again, why the homework is good for you. Let's just say I went with this right here. 4 times 1 over cosine theta. Like I said, I'm pretty sure this is wrong, but I just want you guys to see why this is not correct. Okay, yeah, they gave it to us. But what I would rather you guys do is take this a step further on the left. Get used to simplifying. Okay, this should become 4 sine theta all over cosine theta. Okay, so all I did was I multiplied by the reciprocal of that fraction that I was dividing by. And this is what I have. So now we have all this here, and this is going to help take place to the next step that we're doing. Okay, next part, they want you to simplify the fraction from the previous step such that both fractions have common denominator of cosine theta. Okay, so this might have been the way they wanted it to be. Okay, we see it because the next step is they wanted to be just 1 fraction of cosine. That's what I did right here. So we were actually in good shape that we did it the way we did it. And there we have that. And then last part, we want to make this, and oh, that's supposed to be positive. Now you see why I worked down? Because I'm wondering why is this negative? It should have been positive because of that one right there. But now we have a common denominator. We take 4 sine plus 3 sine, and we get 7 sine theta. And they ask you which expression from the previous step then simplifies it into what? Well, and if you know these, okay. So it's not addition and a Pythagorean identity. It's not that. It's not addition of a reciprocal, that. It's just simply an addition and quotient identity, I'm guessing. Yeah, it's not exactly clear. They didn't cancel. You didn't have a Pythagorean. You didn't have a reciprocal. Oh, I'm sorry. No, they want tangent. That's why. Okay. Okay. So what did we do? We added first, and then we did the identity. And which identity was it? It was your quotient identity. Okay. So they all have the addition. That was this step right here, because they're doing 2 steps in once. Then how did they go from here to here? We use the fact that tangent theta equals sine over cosine. And if you remember the names of those, remember from the PowerPoint earlier from last week, that's not a cancellation property. It's not a Pythagorean identity. Remember, those are squares. It's not a reciprocal because a reciprocal is like sine equals 1 over cosecant. It's not an even odd because we don't have a negative. It's the quotient identity, which means one trig function is a division of 2 others. That's where we get the A from. Okay? So a little bit, some of these last parts, you may have to go back if you forgot the names of them. Like, well, I know the identity, but I don't know what it's called. Go back and look in your notes real quick, or look in the PowerPoint, or look in your book, and you'll see it right there. All right, let's look at number 31. Do a couple more of these. All right, verify this identity. So kind of look ahead and say, I'm gonna do the same thing before. I'm gonna work on the left side. I'm gonna work with the left side, and I'm gonna put it here in this space. And they sort of tell you by their first step right here, it's like, oh yeah, we are working on this side right here. And I'll let you know you pick the correct side. Plus, it's easily the more complicated of the two. Okay, now what's nice of this is, remember, we're looking for secants eventually. Now, what I like about this one is it sort of also gives you a hint if you're stuck where to go. All right, start with the more complicated side, choose the correct transformations, and then we want to rewrite this as 1 plus something. Okay, now they say do not factor. The only thing that changed here, notice, is this tan square. We have the 1 still there. We have the secant theta plus 1. We have to rewrite something here for tangent. Okay, so that's a tough one. There's a couple options. I can rewrite tan square as sine square over cosine square. Now, as much as this will be true, it's not going to help us too much in what we have here. Okay, what I am going to focus on is anytime you see a square function, you think of Pythagorean theorem. And remember this one, tan square plus 1 equals secant square. Therefore, I can replace tangent square with secant square theta minus 1. That would be a good first step. And if you're already looking down a couple steps after this, you might see what we're going to do next. Okay, but this is what I'm going to go with here. Secant square theta. Oh, don't forget your minus 1. And we did that with a Pythagorean identity. And that's what they wanted. Now, what I should have done is, if you were stuck, they give you a couple of options. So this is kind of a way I'll tell you to cheat a little bit and say, okay, if I didn't know where I was going next, like if I look at this and say, I'm not sure what they want, I got to somehow change this. I don't know what to do with it. Look at the 4 choices, the justification, and maybe one of those give you a hint. Divide out the common factor secant. See that? Factor out the numerator, maybe. Divide common factors by secant. Apply the quotient identity. Doesn't look like it. It's this one, though. It's going to be factor out that identity, factor out that numerator, because if you look at that top, nothing on the bottom changes, not that 1, but this is a difference of 2 squares. Oops. Secant theta plus 1 and secant theta minus 1. And that's what I'm going to do here. Because I do that just going ahead. In the future, I'm going to cancel those factors right off. And like I said, I can go ahead. I can go parallel to these steps. Maybe if I see some steps, I'm just going to keep working here on the right. And I'll come back and answer the question in a second, because I know I see the finish line. 1 plus secant theta minus 1. That's all I have left over here. And then these 1s cancel off, and I'm just at secant. And remember, that's what we needed here. So I've proven the identity. Now I can go back, and this might be easier. Factor the numerator. Well, that already did was secant theta plus 1 and secant theta minus 1. Check it. We're good. Third step. All this becomes secant. How? Well, let's see. What did I do? Applied an even odd, applied a quotient, divide out common factor, and simplify. Yeah, and I think that's the one we did here, because let's see. We didn't apply a reciprocal identity. And you look, what I'm talking about is from this step right here to the end. We canceled something. Okay, so how do you cancel? You didn't do an even odd. It was not a quotient identity. It was not a Pythagorean identity. It was dividing out a common factor. That's what we did by slashing these out. We divided them away, and then we simplified by combining the ones, and there's our answer. So it's kind of a puzzle sometimes that you have to figure out. And the good news is it does help you get stronger at these. It makes you get what you need to do. But you have to you got to give this process a little bit of a chance. You have to work on this. You can't just do this all in one day, as I always say. Got to do a few of these, and then you'll get the hang of it, and you'll start to see that there are patterns. There are, ways to handle these. It really does. It's just a way to test that you really know how to do these identities. Okay, let's do a couple more of these here. So I'm going to work on, again, the left side of this. And let's see what we have. We have a secant theta plus cosine theta all over a secant theta minus a cosine theta. Okay, so now, maybe you know where to go, maybe you don't. Let's look at what they say. All right, to establish identity, start with the side containing that. And now they give you some options, which is nice, and the justification. Can I do a reciprocal identity? Can I do a Pythagorean identity? Now I'll stop with this one and say it can't be a Pythagorean identity because all of those are squares. So it's not that one. It's not an even-odd identity because all those have negative theta. So those are gone. It's either a quotient identity or it's a reciprocal. Now remember the quotient identities, the only ones are cotangent equals cosine over sine and tangent equals sine over cosine. So those are the only quotient identities. We don't have any of those here. So it looks like it's got to be a reciprocal identity. And the only reciprocal I can think of, or at least kind of goes with, not the only one I can think of, but what usually goes hand in hand with these problems, let's make these sines and cosines. So I'm going to replace both of those secants with 1 over cosine. Let's see if one of those matches what I had. That looks like it right there. There's my first part. Oh, what did I do wrong? That isn't right. Should be a minus on the bottom. Okay, let me make sure I wrote this problem correct. Yes. That should be 1 over cosine plus cosine. Oh, there's another choice. That's what my problem was. I'm sorry, you guys. I only picked up 3 here. I'm like, okay, I just jumped the gun. Good lesson. Don't just pick something that looks like what I had. I did notice these negatives or positives are off. That's the one right there. 1 over cosine plus cosine, 1 over cosine minus cosine. And it happens when your window is not big enough here. Now we're good. Okay, next, multiply by a well-chosen 1. Okay, now when they say a well-chosen 1, here's what they're saying. I'll give you a better example here. This does not have anything to do with the problem, but okay, what this is if I have this fraction, I can multiply top and bottom by 14 to make everything cancel. What happened was I multiplied the top by 14, the bottom by 14. It's like I multiplied by 1. That's all it means. When they say a well-chosen 1, it means you're multiplying something to the top and the bottom to get rid of things, to cancel, but it's the top and bottom of the big fraction here that we have. Okay, it could be of any fraction. So think of, what am I trying to get rid of? That's usually what you're going to multiply by. And in this case, I want to get rid of those little denominators. So I multiply top and bottom by cosine. So what happens is, this gets a cosine. This gets a cosine, but it doesn't cancel. This gets a cosine, which cancels, and this gets one. And ultimately, we get a 1 plus cosine square theta all over a 1 minus cosine square theta. So that's the well-chosen 1 is the cosine over sine, and the cosine over cosine, and it looks like we're going to multiply this one. Okay, this is, and this is kind of a weird problem, is it's what you had a second ago. 1 over cosine plus cosine, 1 over cosine minus cosine. and we multiply top and bottom by cosine over cosine. That's my well-chosen one. And now, what does it become? Now I'm kind of ahead, that's fine. It becomes that, and how did we do it? Well, think of what happened. It looks like I applied a distributive property because I took this cosine and distributed, not a reflexive, not a quotient, not an even odd again. Looks like it's distributive. Distributed the cosines throughout. That's what I did in pink there. And the last, they get all this, and I didn't have that on mine. But how do I get there? I have a 1 plus cosine square theta all over sine square theta, because I remember that bottom 1 minus cosine square theta is like my Pythagorean identity, and there's our answer. So you see, if you can do the stuff that I have on the right, you'll be able to answer all these questions. Okay, so I almost can do these without looking at this window here on the left, like I was doing. I can get rid of this and just work the problem out and then bring it back in to answer the questions. But what's nice is if you get stuck anywhere, it sort of guides you along. It gives you some hints, or at least it gives you a couple of options. Okay, so that was, I think, number 35. Let's look at number 39 here. Establish this identity. So, same song and dance here. Do a couple more of these just to make sure you guys are on board, because these, as you see, they take a little while to work, depending on what you have. Okay, so we eventually want this to equal cosine theta cotangent of theta. So we're going to work on the left side right here, based on what you see here in these answers. So now, how am I going to establish the identity? I'll just kind of look at this. Like I said, let's get rid of this for a second. Okay, let's just move that off screen. And I'm going to say, well, what can I do? I can do the sine cosine approach. Let's make that 1 over sine minus sine. Sorry for the mess on the screen here. Then I can look at, well, now remember, it's a separate piece. Don't mess with the right side. But maybe I need a common denominator here. So let's put a sine here and a sine here. That gives me a common denominator of sine. And now on the top, I have 1 minus sine square theta. And then I can rewrite that as cosine square theta. You see how many times we use that one particular Pythagorean identity. And then now, I'm kind of done, except go back and look at what you're looking for. They want a cosine and a cotangent. Okay, so I can take these two cosines, a cosine square, and I could see, well, there's my first cosine, that's good. And what do you know? That becomes a cotangent right there. And now I have exactly what I'm supposed to have. Okay, so I was able to do this all without, looking at their sheet, because sometimes their choices confuse some of you. I'll admit that, it confuses me. So now I want to look at which one best represents my way that I did it. We had a cosecant minus sine. I rewrote that as 1 over sine. Okay, well, 2 of these have 1 over sine minus sine. 2 of them don't. So I'm already going to say goodbye to this one and goodbye to that one, because I don't have a 1 over cosine, it's 1 over sine. Okay, so those are good. Now let's look at the next part. Here's what they have, or that one right there. Let's see which one most looks like my next step around there. And they're a little different than mine. You can see where this is, sorry, I boxed too much. This is the next step right here. That and that, which one most looks like mine? So I'm looking through, that's the part I'm trying to match. I have a cosine square of a sine. Here they have it, but here they have a negative, which leads me to think this is not right. So let's just keep going though. Then we have a cosine times cosine over sine. Got that right here. And then we have a cosine cotangent. Got that here. So you see how these all match mine? There's my answer. And it's usually a process of elimination. And yeah, you might have been able to do this problem a little faster if you didn't do all the steps, but there it is. Okay, the real test that they're asking is, can you do these identities straight up? It's just kind of hard for a student to do them in a computer graded assignment. So that's why they answer them this particular way. Okay, so same thing here. We have three parts. They want you to take the left side, it looks like, use a Pythagorean identity to rewrite the numerator in terms of cosecant and cotangent, and factor the denominator of two factors by factoring the difference of two squares. Okay. Okay, let's just look and see what we have here. 1 plus 2 cotangent square theta squared all over cosecant fourth theta minus cotangent fourth theta. Okay, now, like I said, sometimes in reading this, I confuse myself because I already think I knew how to do this, but now that got me thinking about something else. Use the Pythagorean identity to rewrite the numerator in terms of cosecant and cotangent, and factor the denominator into two factors by factoring the difference of two squares. So I can do the denominator easy. That's going to be cosecant square theta plus cotangent square theta times cosecant square theta minus cotangent square theta. Okay, on the top, I think I know what they want. So if you remember your other identity here, remember cotangent squared plus 1 equals cosecant squared? Okay, remember that identity? The third Pythagorean identity, the one that you probably will use the least. I'm going to use that, and it's a multi-step part here. I'll admit it's not a one and done. So let me show you which one I'm pulling out. You guys see? Sorry. Okay, remember from today's lecture, the very beginning, we went through our Pythagoreans. Remember these right here? That cotangent squared plus 1 equals cosecant. That's what I'm using right now. Okay? Now, how do I use that up top here? So, let me do it right here. Just the inside of that top parenthesis, we have 1 plus 2 cotangent square theta. I'm going to rewrite this as cotangent square theta twice. So you see that? 2 cotangent square theta is a cotangent square theta plus a cotangent square theta. This right here is this, and that's going to become the cosecant squared. So that's what I did. I took one of them and made him a cosecant squared theta, and I'm left with another remaining cotangent squared theta. That right there, this box became cosecant, and then we left with one right there. So that's how I ended up at this step right here. So I think that's what they're talking about. We'll find out in a second where they say, use a Pythagorean identity to rewrite the numerator in terms of cosecant and cotangent and factor the denominator into two factors by the difference of two squares. So this should be the line that I have right here. And if we have identified exactly what they're talking about. So we have cosecant square theta plus cotangent squared theta. And remember, that whole thing is squared on the top. So on the bottom, we have a cosecant squared theta plus cotangent squared theta. And a cosecant squared theta minus a cotangent squared theta. And that's what they wanted. Now we're going to cancel the common factors. Now this one's a little bit weird, but let me just rewrite that top so that everyone is 100% clear on what that is. When I have a parentheses squared, remember, it means I have two of the same parentheses. So cosecant plus cotangent twice is what I have. So I'm going to, and that's all over the one that we had before, which was a cosecant squared theta plus cotangent squared theta and a cosecant squared theta minus a cotangent squared theta. So we cancel our exact same parentheses, which is this and this. And after you cancel, use a Pythagorean identity to rewrite the denominator. Okay, so the denominator is cosecant theta minus cotangent. Remember that identity I wrote earlier? Cotangent squared theta plus 1 equals cosecant squared theta. I can subtract the cotangent over here, and you notice it'll look exactly like that. That's going to be the number 1. So what that'll give me is just that numerator. Cosecant squared theta plus cotangent squared theta. Uh-oh, what did I do wrong here? Cosecant squared plus cotangent squared. Oh, write the new denominator below. That's nice. Just the 1 is what that whole denominator. This canceled became nothing, and that became a 1. Now the entire expression can now be written as this, because what I didn't show here, what I was starting to type in there, is all we have left is this. Now we have to make it become this, 2 cosecant squared theta. So I've got the cosecant squared theta right here. I need to get rid of this. Once again, I'm going to use the identity. This stays, and this becomes cosecant squared theta minus 1. Okay, you see this identity right here? Move the 1 over so it becomes a minus 1, and we get the cotangent. Gone. So that's how we do it. And then these 2 cosecants become 2 of them. So we're going to use another Pythagorean theorem identity, and we have our answer. Okay, I think you got enough of these for today. I mean, there's only one more that I was going to do, but I know there's only so many you can watch me do, and then you're going to start to either get it, you either have it by now or you don't. So I want you to just kind of work on these. This one right here, don't worry if you don't get to 47. We can pick up with this stuff on Wednesday. For now, I just want you to get going on this homework. If you have not finished homework number 4, obviously that should be done ASAP, and do that quiz ASAP. So then you can focus on this number 5, because as you see, this takes a number of steps. It's not exactly the most clear every time. So I want you to start working on this. And if you make mistakes, you can correct them, you can amend them, and you can get better at it. And then get on that quiz as soon as you can. This one's due on Friday, but I don't want you to wait till Friday, quite honestly, because there will be it's not going to be easy. So on Wednesday, I will finish up any loose ends we have from number 7.4. I may even briefly look at the quiz, and then I'm going to start 7.5 and 7.6 on Wednesday. Get us through some homeworks there, get us ready through, to finish up on Friday. So any questions, shoot me an email or stick around here. And other than that, have a good day, and I will see you all in 2 days from now. So have a good one.